Hi again. So we're in the middle of thinking about how to describe data types. And we ended up in this place where we took an example of natural numbers and we managed to simplify the description to having exactly one constructor, where inside that constructor we had the Boolean making us choose between the previous constructors, and having exactly one argument, which we did by packing up all the arguments in a sigma type. So taking a pair of things rather than taking two separate things, right? And then we saw that this data type of the natural numbers was completely described by this operation from set to sets. So if we want to describe data types in general, then we need some way of describing operations from set to set. In the case of simple data types such as natural numbers. Things become more complicated if you want to treat vectors, etc. But let's just deal with simple things for now. So we want some way of describing operations from set to set. And then we say that there's certain things that we need to do, right? So we need to be able to take a sigma type over something which previously existed, and then the rest of the argument depends on what this b is, right? So here we're using an if to deliver the rest of it. So that's one thing we need to do. We also need to be able to stop by just saying, okay, this is trivial now. We need to be able to do these recursive occurrences of x was the placeholder for the thing we're currently defining, right? So we need some way of referring to that. And you can't see it in this example, but we also need to be able to take something times something else. So if you have binary trees, for example, then you want to have a left subtree and a right subtree, which will be represented by x times x, right? So here is that pattern described in one data type. So I have trivial stop, sigma types, products, and placeholders. And most of these are kind of self-explanatory, I think. So this one takes no more arguments. If I'm taking a product, then I have to describe the things I'm taking a product of. And if I if I have the variable, then I don't need anything more. But the sigma is a bit strange. So here first we have an a which is in u, whatever that is. And then here we have another description which depends on the elements of a, whatever that is. So u here is a small representation of sets. So it's u for universe. And L tells us for every representative in this U which set it represents. Right? So you could see this as a set of codes for types, and L is the decoding function which tells you what types they really represent. Right? And I'm doing this for two reasons. Partly because I'm trying to be size conscious. So I want this to be a set, which means that I can't quantify over all sets here, because then I would get Russell's paradox. So I'm just quantifying over certain small sets that are represented in this U. So that's one reason, and the other reason is that I want to be able to limit this U to a smaller class of things later, so that I can say something about it. Okay, and then the claim is that these descriptions really represent operations from set to set. So let's see if we can prove this. And I put the brackets in here to emphasize that that's what it is, but of course the brackets are not really needed. Right? We could also see it like this. Okay, so we're taking a set X, and we have to say which set we get depending on this description. So I need a pattern match on the description. And if it's top, then I'm going to return top. If it's a sigma, then I'm going to do something. And if it's a product, I'm going to do something, etc. So let's do the sigma first. So I want this to be a sigma of something and something. Okay, I have to say exactly what it is. So it's an X in the elements of A, because A here was in the universe, right? So if I look at its elements, I get the set. And now here, I want to continue decoding B of X with the same placeholder X. So I'm saying, okay, I have something in the elements of A, so this is the Booleans, and then I continue according to what the rest of my description says. So if this was if then else on this boolean, then that's what I got, right? Okay, and here I want this to be something times something. It's decoding the first thing with the x or decoding the second thing with the x. And finally here, I'm just going to use the placeholder I have. Right. Okay, so this is how I can take each one of these descriptions and turn it into a set transformer. So here's an example. So in order to use this, you first have to decide what universe of things you want to use, right? So I'm going to use a really small one, which contains exactly the booleans. So I'm saying I have the code for the booleans, and the elements of this code are really the booleans. Okay, and then I open this description with this URL, and I'm going to write down a code for NAT. Let's remember what we had before was this. So this is what I want to describe. So I see that the first thing I have here is a sigma. So I get to use the code for a sigma. Okay, and then here I have to say the booleans, but I have, so here I have to give something in U, and I have code for the booleans in U. And then here I now have to say what the rest is based on the elements. So that's B is a boolean, and then I want to say if B, then something else something. Right. And in this case I want to stop. And in this case I want to use the placeholder X. Right. So just basically taking the same thing but written down as a code in this universe rather than writing it down as a set. And if I now decode this, so to args of NAT code, then I get the same thing as this function, right? So I can now say that my natural numbers prime is given by one constructor, 0 or sac prime, which goes from args for NAT prime of using the thing I'm defining as the placeholder. And I can now find 0 prime to be something, and sac prime to be something. So here I have to use the constructor and normalize this. I say that I have to give a boolean. If I want 0, then I want this to be true, I think. And then here I have to give top. Here is the other branch, various recursive argument I had. So again, I can make these patterns if I want. Let's get rid of the types. And now I can define my predecessor function. Just like before, with a few more primes. And we have exactly the same thing. But now we have really described the data type using this very concrete code that we can now manipulate and do things with, right? So what have we learned? Well, we can describe operations from set to set, which a priori is a really big space of things, right? By this little data type of the things we really care about. And then we can define a decoding function args, which takes our small description and turns it into what it really represents. And right, so here I did this for the natural numbers, but we can do this in general, right? So let me actually do that up here, where I can define a data type for a given description. So if D is a description, then I get the set where I have one constructor from args of D. And now for the placeholder, I'm going to use the thing I'm currently defining. If I have that, then I get something in. Okay, so then, so this is a generic way to get the data type out of a description, right? Saying that, well, we have one constructor and the arguments are given by this args function. So now let me go back and change this. Don't need this anymore. I can define this generically as the interpretation of NAT code. And the only difference is that all my constructors are now called con. Right. So now we're using the generic one. So for every description, we get exactly one data type, which we can now describe generically, like this. So that's really useful if you want to prove something about all data types, because now we can just prove something about all descriptions, and then we get to prove something about all of them of this shape.